Hello, so this is a revision video for AP Chemistry 1.7, Periodic Trends. The periodic table in chemistry shows repeating patterns in chemical and physical properties of the elements, known as periodicity. These patterns are explained by electron configurations and the arrangement of electrons in energy levels and sublevels. Elements in the same group, or vertical column, have similar outer electron configurations, giving them similar chemical properties. They have the same valency, number of electrons in their outer shell. Across a period, or horizontal row, the number of protons and electrons increases, affecting atomic properties in predictable ways. These trends are largely due to the number of electron shells increasing down a group, the effective nuclear charge experienced by the outermost electrons, which increases across a period, and shielding by inner electrons, which also increases down a group. These all link together to affect the strength of attraction between the nucleus and the valence electrons in an atom, and can be explained using Coulomb's law, where the force of attraction is proportional to the charge of particle 1 times charge of particle 2 divided by the distance between them squared. As nuclear charge, so the number of protons in a nucleus, increases, the attraction to outer electrons increases, unless offset by shielding from inner electrons. For example, ionization energy, the energy required to remove an electron from an atom, increases as a general trend across a period from left to right, and decreases down a group from top to bottom. This is because across a period there are more protons in an atom's nucleus, meaning a stronger effective nuclear charge and stronger attraction between the outer electrons and nucleus, making them harder to remove. The number of inner electron shells remains the same across a period, meaning the inner shielding doesn't change. However, down a group, more inner electron shells means more distance and more shielding between the outer electrons and the nucleus of the atom, making the electrons easier to remove because they experience less attraction. Notice here that the positive charge of the nucleus does also increase down the group, but it doesn't increase enough to offset the increased distance between the outer electron and nucleus. The atomic radius, so distance between the nucleus to the outermost electron, decreases across a period and increases down a group. This is because, for the same reason as ionization energy, across a period, increase in nuclear charge pulls electrons in the atom closer to it. This decreases the overall size of the atom. Down a group, however, new energy levels are added, making the atom larger, increasing the inner electron shielding, moving the outer electrons further away from the nucleus. Ionic radius refers to the distance between the nucleus and outermost electron in an ion. Cations, positively charged ions, are smaller than the atoms that they form from, because they experience less electron repulsion. Anions, negatively charged ions, are larger than the atoms they form from because they have more electrons in, causing more electron repulsion. As a result, the ionic radius trend across a period actually changes. For example, in period 3, the ionic radius decreases from Na+ to Al3+ as the nuclear charge increases, whilst the number of electrons stays the same. The ions all have the same electron configuration. This greater attraction from the nucleus pulls the outer shell of the ion more tightly, decreasing the ionic radius. There's then a noticeable jump in ionic radius between Al3+ and P3- due to the switch from positively charged to negatively charged ions. Then the ionic radius decreases again as the ions get less negatively charged, causing less repulsion in the outer shell. Notice that silicon and argon in period 3 don't readily form ions and so don't have an associated ionic radius. Electron affinity, the energy change that occurs when a gaseous atom gains an electron, becomes more negative across a period and becomes less negative down a group. This can be explained as a greater attraction between the nucleus of an atom and an incoming electron as you go across a period, and a decrease in attraction as you go down a group. Note that there are some slight exceptions to this trend, which are usually explained as atoms having filled sublevels, so incoming electrons experience less attraction to the nucleus. Electronegativity is the power of an atom to attract electrons to itself. As a general trend, it increases across a period from left to right and decreases down a group from top to bottom. It's a relative value and doesn't have units, with the most commonly used scale being the Pauling scale, with fluorine having a Pauling value of 4.0, the most electronegative element on the table, and the group 1 metals having the lowest electronegativity values, 0.7 to 1.0. The electronegativity increases across a period because the atomic radius decreases and nuclear charge increases, but the shielding stays roughly the same, so the nucleus is able to better attract an electron towards the atom. Down a group, however, atomic radius and shielding increases, so it's harder for the nucleus of an atom to attract electrons towards itself. The effective nuclear charge, or ZF, of an atom is the net positive charge felt by an electron after accounting for shielding by inner electrons. It helps explain the periodic trends outlined previously, like atomic radius and ionization energy, where ZF equals actual nuclear charge minus shielding from inner electrons. As effective nuclear charge increases, electrons are held more tightly, meaning higher effective nuclear charge means a smaller atomic radius and higher ionization energy, and a lower effective nuclear charge means a larger atomic radius and a lower ionization energy.